We now discuss the solution of a problem from the section Abstract Algebra, and this question has appeared in the CSIR National Eligibility Test held on 16th September 2022. The problem is related to the nilpotent elements of a ring, and this question is from the subsection ring theory. The given question is, let R be a ring and N be the set of nilpotent elements, that is, N is equal to the set of all those elements x belongs to R such that x power n is equal to 0 for some natural number small n. Which of the following is true? We are given four options. Option 1, n is an ideal in R. Option 2, n is never an ideal in R. Option 3, if R is non-commutative, n is not an ideal. Option 4, if R is commutative, n is an ideal. We have a ring R and n is given to be the set of all nilpotent elements. Then we have to discuss the validity of the four statements given in the options. So that's our given question. Let's now discuss the solution of the problem in detail. We are given R is a ring and N is the set of nilpotent elements, that is, the definition is also given here. N is equal to the set of all those elements x belongs to R such that x power n is equal to 0 for some natural number n. Now, notice that 0 belongs to n. How? 0 power 1 is 0. Therefore, 0 is a nilpotent element. That means in any ring R, 0 is always a nilpotent element. So this tells you that n is a non-empty subset of R. Agreed. Then what is this n? Is it an n an ideal? If it is so, under what circumstances? If it is not an ideal, then when it is not an ideal. That's what you have to do it. Now, we make a hunch that if R is commutative, the option 4 is true. If R is commutative, N is an ideal. So let's see whether our hunch is true or not. Agreed. So that is our statement of the option 4, and R is a commutative ring. Now our hypothesis is R is commutative and N is the set of nilpotent elements of the ring R. Then we have seen N is a non-empty subset of R. Now one may ask a question that how did you make a hunch that R could be a commutativity? Because of the presence of course, because of the one also, from the ideal test also, we can do. From the test 2, the ideal, from the second property of the ideal, from the ideal test is RA belongs to U for all R belongs to R and A belongs to U. That means in our case, for all R belongs to R and X belongs to N, then Xn and to the power of Xn to the power of something is equal to 0. Xn, that means Xa, Xr to the power of N is equal to X power N. R power N is possible only when R is commutative. That is why we thought that R is commutative will work here. And anyway, to say that N is an ideal, we recall the ideal test here. So we verify the first condition. Let xy belongs to n, that means x and y are nilpotent elements, and x power m is 0 and y power n is 0 for some natural numbers m and n. Agreed. So to satisfy this one, x minus y must belong to n. Now x minus y to the power of n plus m, we do it. That will be equal to, and the binomial theorem holds here because r is commutative. So sigma r is equal to 0 to m plus n CR into x power m plus n minus r into minus y to the power of r. Yeah, this binomial holds because of the commutativity, they will come like this. Otherwise, the elements will be written separately. But the commutativity is there, they commute, therefore it comes out like this. So binomial theorem is valid in a commutative ring. Agreed. Now, first sum it up from r is equal to 0 to n minus 1. 0 to n minus 1. Minus y to the power of r is written as minus 1 to the power of r into y power r. M plus n CR into x to the power of m plus n minus r. Now r ranges from 0 to n minus 1. When r ranges from 0 to n minus 1, m plus n minus r is greater than m. Is greater than m. When x power m is 0 and m plus n minus r is greater than m, therefore x to the power of m plus n minus r is 0. Plus the nth term we will write minus 1 to the power of n into m plus n, r is n, x power m, y power n. Agreed? This is the nth term. So x power m is 0, y power n is also equal to 0, this is 0. Plus the remaining, that means r is equal to n plus 1 to m plus n. Then in that case y power r, so that means for r ranging from n plus 1 to m plus n, r is greater than n, and y power n is 0, y power r will be equal to 0 because r is greater than n. Agreed. So that means each is equal to 0. So 0 plus 0 plus 0, that is equal to 0. So this tells you what? This tells you x minus y is a nilpotent element, therefore it belongs to n whenever xy belongs to n, for all xy belongs to n. Thus our first property we have verified. First property of the ideal is verified. We continue in the next slide. So this is our second condition. So second condition is let R be an arbitrary element in R and X be any element of N. X is an element of N means X power M is equal to 0 for some natural number M. Now we take Rx to the power of M. That will be equal to R power M into X power M because R is commutative. This is the hunch. This is the hunch. So this is the hunch of what we have made, an expectation what we have made because of the R is commutative. This will come. For that reason, we started doing this one. So R power M into X power M, and R power M into X power M is 0. So it is 0. So that means Rx belongs to N for all R belongs to R and X belongs to N. And since R is commutative, Rx is equal to XR, and XR also belongs to N. R belongs to R and X belongs to N. So thus what we have proved is Rx belongs to N and XR belongs to N. For all R belongs to R and X belongs to N, the second condition is satisfied. Thus N is an ideal in R when R is a commutative ring. So therefore the option 4 is true. So that is the detailed discussion of the solution of the problem, which is from abstract algebra, and it is from ring theory, and which is related to the nilpotent elements. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.